Okay. So far what we have done is we have seen a vector analogy and try to put that into signal space. Okay. So we are now targeting that a particular signal must be represented by another signal, and then from the vector analogy we also know that in the signal space, if we can now, we also now know what is the characterization of orthogonality of two signals. So in a particular signal space, if we can find out all the set of orthogonal signal, then we know that exactly a particular signal can be represented in a linear combination of all those orthogonal signals. This is something we have already understood, and their linear coefficients also, how to calculate that also we have characterized now. Okay, so we know that exactly how to evaluate those optimal C, which minimizes the whole error, and if I have that complete definition, that is called the completeness of the basis set. So if I have complete definition of all the basis set that are possible in that particular signal space, I will be able to represent a signal. So this is what Fourier means. This was the background where Fourier started means analyzing signal, and this is how he started things. So let us now, our now target should be that how do we represent or how do we find out all the orthogonal signal in a particular signal space. So initially Fourier started with trigonometric signal or sinusoidal signal. So he initially started with, let us say we take this cos m 2 pi f0 t. Okay. So he started with this, and correspondingly I can also define a sin m 2 pi f0 t. Okay. So these two signal we are targeting. So whenever m is equal to 1, it is just a cosine signal with frequency f0, where f0 is equals to 1 by t0. Okay. So t0 is the time period of that signal. So whenever we are talking about cos signal or sine signal, it is a periodic signal, we know that. And the thing is that if the constituting signals are periodic, then what it will represent must also be a periodic signal. So what initially Fourier devised, he told that okay, I can represent signals, but all those signals must be also periodic signal that I am targeting to represent. That can be any signal, it might be a triangular wave, something like this, let us say this kind of thing, but it must be periodic with period, let us say t0. It must be a pulse, and of course it gets stretched to minus infinity. So it can be any periodic signal, and he then started saying, can we represent this in a particular fashion, and then he started inquiring the basic signal that we know, even the electromagnetic wave that propagates with this cosinusoidal or sinusoidal. So can we represent all these signals with respect to this cosinusoidal or sinusoidal? But before doing that, we need to know the orthogonal signals in that signal space. So what he started doing, he started inquiring whether two cosinusoidal, let us say cos m 2 pi f0 t for different values of m. Okay, so let us say one is cos m 2 pi f0 t and another is cos n 2 pi f0 t, whether these two signals are orthogonal or not. So if they need to be orthogonal, what we have to prove? It is a real signal, cos is a real signal. So all we need to prove is, and it is a periodic signal. So within one period, if the property is true, it will be true for all other periods, because it will be just mimicking the similar pattern. So orthogonal means the integration must be 0, right? Their multiplication and integration must be 0. That is what we have understood. G and x will be orthogonal if gt into xt dt over a particular time period must be 0. So if within one period it is 0, the other period also will be behaving similarly. So entire period or entire signal duration, it should be 0. So this is what we wish to prove. Is it true? So we will probably do it from, let us say minus t0 by 2 to plus t0 by 2. We can even do it from 0 to t0, any period you can take, even we can do it from t0 to t0. So, over a single period we are trying to evaluate what will be happening if we do this integration, because we know that that is the proof of orthogonality. If this is 0 for two different signal, of course, if it is same signal, then we should not, we should get the energy back, right. So, if it is two different signal, that means two different values of m and n, or we are saying m not equal to n. For this condition we are trying to see what will be the value. Okay. So, let us see, let us try to evaluate this. Take out half, it should be, or I can do it over here only, half 2, right. Now, just put a trigonometric form, 2 cosine into cosine. So, that should be cos a plus b plus cos a minus b. So, it should be cos m plus n 2 pi f0 t plus cos m minus n. We are assuming that of course, cos negative that will again become positive. So, here either m is bigger than n or n is bigger than m, it does not matter, it will all be same. There is a half outside. Now, let us see the first integration, 0 to t0 cos okay. So, if m is not equal to n, then both these numbers are non-zero. Okay. So, what is happening, this is another cosine, and whatever that f0, this m plus n or m minus n, it will be either 1 or bigger than 1. So, over that period t0, if I integrate a cosinusoidal, which is, see, already 2 pi is there, that means either it will just make the full cycle or it will make multiple full cycle. And a cos signal, if it completes a full cycle or multiples of full cycle, always the integration, what will happen, sorry, up to this, always the integration will be 0, right, as long as it is a cosinusoidal signal, and we know that it is either completing a full cycle, if the difference is, let us say, this addition, of course, it will not be, it will be more than a full cycle, it will be 2, 3 or some integer number. So, multiples of full cycle it is completing. So, if I integrate, that should be 0 definitely. So, this part will be 0, even this part also will be 0, because it is either it will be 1 full cycle, because m not equal to n. So, m minus n at least it will be 1, and it might be even bigger than that. So, whatever it is either a full cycle or multiples of full cycle. If I integrate again, this will be 0. So, the overall thing will be 0 if m not equal to n. So, therefore, we know that all the cosinusoidal signal with all values of m going from 1 to infinity are all orthogonal to each other. That is a very important findings. So, what he could find in that signal space, in the vector space, if you remember, when we had this page 2 dimensional, we had only 2 orthogonal vector. Now, we actually have infinite orthogonal vector, right. Any value of m you put, so m starting from integer value, of course, starting from 1 and then going up to infinity. Any value m or n you put, as long as m not equal to n, all of them are actually orthogonal to each other, and these are actually called the harmonics. Okay. So, you have a cosinusoidal, you have twice frequency cosinusoidal, thrice frequency cosinusoidal, and so on. All those frequencies or all those harmonics, first, second, third, fourth, all those harmonics are included, and they are actually orthogonal to each other. That is one finding. The second part is, if I have a DC value which is just 1, okay. So, between that 0 to t0, whatever period I have talked about, so it just takes value 1. if this is the case, will this be orthogonal to all those costs? Of course, because what will happen? This has to be multiplied with those costs and again will be integrated. So, if I just do that, integration should be 1 into cos m 2 pi f0 t dt and integrated over 0 to t0, right. So, now again it is a cosinusoidal with m taking value 1 to infinity. So, therefore, this is actually because the 2 pi is already there and f0 is 1 by t0. So, basically this is either a full period or some multiples of full periods. So, it will always be again integrated to 0, right. So, even this particular signal where it is just taking a constant DC value, that is also orthogonal to all those cosinusoidal. So, the DC value which for a single period it takes same value. So, if I just consider all the periods, it will just take a DC value. So, the DC value even is orthogonal to all the cosinusoidal signal, right. So, this is what we have already demonstrated. Now, the next part is this also orthogonal to, of course, the DC as well as all those cos values. We will now again show that if I multiply with some cos, let us say n 2 pi f0 t for any value of m and n. Now, we do not have a restriction because even if m and n are equal, these two are two different signals. Okay. So, if I just do this integration, again you will see with the same logic, it will again become some cos or sine, and then within again some either full period or multiples of full period, the integration has to be done and it will all be 0. So, therefore, what we have done is we could identify now few mutually orthogonal signal, and I should not say few, it is infinite. Okay. So, all the cos m 2 pi f0 t for all values of m positive integer, all the sine 2 pi m f0 t for all value of m positive integer, and DC value. These are all these infinite number of signals are all mutually orthogonal to each other. The other part which I am not covering over here, which is a little bit more involved, that if I take this whole set, that is a complete set of bases. Like that two dimensional vector we were saying x and y, that makes it complete, because only with those two vectors I can represent any vectors. In this signal space for periodic signal, we can actually prove, which will be a little bit more involved. So, we are just giving the outcome that if I just consider these basis set, this actually makes a complete basis set, because these are all the basis set that can be defined in this particular representation. Okay. So, if I consider all of them, I could actually finish representing all of them. Okay. And any periodic signal therefore should be means we should be able to represent any periodic signal with respect to these basis functions therefore. Okay. So, what should happen then? I know that now my any periodic signal GT, I should be able to represent them linear combination with the linear combination of all these basis functions, right. So, therefore, I can write first is DC. So, A0 into DC term, which is 1, plus sum AN into cos 2 pi n f0 t, where f0 is actually 1 by t0 and this t0 is the period of this signal. Okay. And I have to take, because all bases should be taken. So, I have to take a summation over all possible cos this thing or all possible values of n. So, n 1 to infinity, plus the sinusoidal is there. So, Bn sin 2 pi, let us say n f0 t summation that is the famous Fourier series representation of any signal. So, because we have proven that these are the basis set which are mutually orthogonal to each other, and because we have also without proof we have stated that these are all that I can get in that signal space. So, this is actually a complete definition of basis set. So, therefore, without error I can be means I should be able to represent GT as a linear combination of all these basis set, where the coefficient of linear combinations are this A0 and AN and BN. Okay. And how do we evaluate these values? Let us say A0, how should we evaluate that? This is something we have already seen. The evaluation of A0 should be with those dot product, right. So, all we have to do is this GT with respect to our whatever signal is. So, therefore, 1 dt must be integrated over a period 0 to t0, and this 1 should be also multiplied with itself. So, 1 into 1 dt from 0 to t0. This has to be done. Okay. So, as long as we are doing this, we will be able to represent the whole thing, right. So, A0 is like this. Similarly, AN must be whatever that GT is, we multiply that with cos 2 pi n f0 t, integration should be 0 to t0 and 0 to t0, it should be cos square, right, cos square 2 pi n f0 t dt. That is the Fourier coefficient. If you go back and try to see whatever you have learned in Fourier series, this is actually the Fourier coefficient. This is something we have already proven. This is the optimal AN for representing that signal. Okay. So, similarly, Bn also will be, we can get a formula of Bn. So, 0 to t0, it can be 0 to t0 or minus t0 by 2 to plus t0, whatever it is, it should be that single period. Okay. The result will be same. So, again GT, this time it should be sin 2 pi n f0 t dt divided by okay. So, in your Fourier transform you might have seen that this happens to be, if you do this integration, it is just 1 or dt integrated 0 to t0. So, that should be 1 by t0. So, A0 becomes 1 by t0, that is the whole formula, right, gt dt over the period. Okay. This if you do integration, it should be t0 by 2. If you just do that integration, there will be a half coming out, then 2 going in, and then if you do that integration, you will just find 1. Okay. So, this should be 2 by t0. So, therefore, this thing goes away, you get 2 by t0, same thing happens over here. So, this becomes 2 by t0. So, that is the famous Fourier series and the Fourier coefficient calculation, which we could directly now prove without any ambiguity. Okay. Is this very clear to everybody? So, once we have done this, there is another representation. Probably whenever we, so this was all fine. We know that any signal now we can actually represent with respect to corresponding sinusoidal. So, what is actually happening? All the sinusoidal harmonics are now coming into picture. So, any sinusoidal means any periodic signal you want to represent, it is nothing but an infinite summation of different harmonics, nothing else. Any signal can completely be represented if you can evaluate through this the coefficients, appropriate coefficients, you will be knowing exactly how linearly you have to combine those harmonics to get this particular signal. So, that is a very nice representation. You actually now know that which sinusoidal with what strength you have to take and you have to add them to get this particular signal. In a way, it is also giving us a strong tool. You get a signal, you immediately know what are the constituent sinusoidal with what kind of strength should be present in that particular signal. Okay. So, whenever we start talking about what are the constituent sinusoidal, That means we are now talking in terms of what frequency components are actually there in this particular signal. This is where a signal gets represented in the frequency domain. Okay. So, if we just give one example, probably we just represent this particular signal. So, the signal is something like this. Let us say it is omega t, it is defined from minus pi by 2 to plus pi by 2. It is like this, and then again this is pi, this is 3 pi by 2, it starts again, this is 2 pi, and so on. So, if I represent a signal like this, which is a periodic signal, and then if the way we have learned to evaluate the Fourier coefficients, if we just calculate that, we can see all the Fourier coefficients, and we can then start representing this signal with respect to frequency component. So, right now I will not give the example fully, because we still have not equipped ourselves fully with the frequency component, but what we will do, we will take this example and come back after little bit of more analysis and come back and draw actually the frequency spectrum. We will see what are the harmonics which are present and how they are present, and accordingly we can actually draw the spectrum of this signal, another representation, not in time domain but in frequency domain. So, basically we will be saying the representation of that equivalent representation will have like this. So, f0 to f0, 3f0, what are the components it has. So, it will just give another representation in frequency domain. So, here it is just f0 to f0, that means frequency is increasing, and what are the components of those frequencies which are present, that will be able to characterize. So, this is how Fourier series actually gives us a frequency representation or frequency domain representation of a signal. It is nothing, it is just, it says for a periodic signal what are the, whenever we say frequency component, we are actually saying what are the basis components that it has, and basis components means it is sinusoidal. So, all those frequency component, whenever we talk about, whenever we plot the frequency domain, we are actually saying at that point there is a sinusoidal, corresponding sinusoidal. Whichever frequency component we take, we say at that point there is a sinusoidal with that strength, whatever strength we will be putting. So, frequency domain representation is nothing but every frequency component we pick, actually there is a equivalent sinusoidal that means that actually makes the signal. So, you take of that strength sinusoidal, you add all of them, you actually get the signal back. So, therefore, there is a equivalent representation, we should say. In time you see, also in frequency domain you start seeing the similar representation of that signal. It is just thanks to Fourier, he could actually give that extra representation of signal, which you will see that which helps us in many way for the processing of the signal. Okay. So, before going into that and before characterizing that, let us try to see another representation which is also a Fourier representation. We have already seen a representation with respect to real signal. So, right now whatever basis set we have constructed, those are all cosinusoidal, sinusoidal or DC value, those are all real signal. Now, what we will do, we take a signal which is a real signal probably GT, but we will try to now represent it with respect to some complex signal. Okay. So, first of all we will try to define a family of complex signal which are mutually orthogonal to each other. Then we will say what is the, again the technique is same, we will then say what is the overall complete basis set, what is the definition of complete basis set. Once we get that, we can get a representation again. So, that particular thing is represented as exponential complex signal. So, it is like e to the power j 2 pi f0 n t. So, this is my test xt. Okay. So, any xt which is taking this value, where n now can take integer, but it can be positive, negative, up to plus infinity, minus infinity. Okay. So, n can now take any value from minus infinity to plus infinity, but it is integer. Okay. Now, let us first try to test whether this infinite number of signals we have got, are they orthogonal to each other or not. So, that is something we have to prove. This signal is a complex signal because we have this complex part already. So, first we have to prove that this is orthogonal or not. So, now we have to employ the complex part or complex equivalent orthogonality criteria. So, that means suppose we take a xt or x1t, which is e to the power j 2 pi f0 nt, and we take another x2t, which is e to the power j 2 pi f0 mt. Okay. So, now all we have to prove is if m not equal to n, then should we get the orthogonality criteria equal to 0. So, what is the orthogonality criteria? That is actually x1t into x2t star. So, therefore, it should be e to the power j 2 pi f0 nt into the complex conjugate of this one. So, that should be e to the power minus, complex conjugate of exponential is just minus of that, e to the power minus j 2 pi f0 mt dt. And if you carefully see, this is a complex signal, but this is also a periodic signal, because this signal can be represented as a complex cosinusoidal and sinusoidal. So, it should be cos this particular factor 2 pi f0 nt plus j sin 2 pi f0 nt. So, therefore, again the fundamental frequency is related to this f0, which is equal to 1 by t0. So, the integration needs to be just done over that fundamental time period. We do not have to do that whole integration, because we know that in one integration if we can prove, this just gets repeated. So, same technique we will be employing. So, 0 to t0 we can integrate the same signal. Okay. So, now this is, let us try to evaluate this. So, it should be 0 to t0 e to the power j 2 pi f0 m n minus m t dt, right. Now, this integration, how much it should be? It should be just e to the power j 2 pi f0 n minus m t divided by the coefficient j 2 pi f0 n minus m, and then we have to put value 0 and t0. Now, see, if we just put t0, t0 is 1 by f0, right. So, this gets cancelled, n is not equal to m, right. So, this must be, this cannot be 0, right. So, this must be some positive integer. Okay. Therefore, it is just e to the power j 2 pi into some integer, e to the power j 2 pi into integer, right, that we can represent as cos and sin. Now, cos 2 pi integer plus j sin 2 pi integer, cos 2 pi integer, that should be always having value 0, right. So, what do we get? If I just represent this, so it should be, so if I just represent this, it should be, sorry, cos 2 pi, that should be 1, right. So, we get 1 for t0, and then for sin it is 0. So, j part is cancelled, minus I have to put this limit. So, again I put 0, it should be 1, and for sin it will be 0. So, 1 minus 1, it gets cancelled. So, this becomes 0, right. So, whenever m not equal to n, it is always 0. If m equal to n, this becomes already 1, right, because it becomes e to the power 0. So, we know that this particular things are all orthogonal as long as m is not equal to n. That means it is not, of course, with himself it cannot be orthogonal. So, with all other signals, they are mutually orthogonal to each other. So, this is something we have now proven. Any value of m and n you take, as long as m is not equal to n, we could, from the basic principle of orthogonality of the complex signal, we could prove that they are all mutually orthogonal to each other. And again we are saying that we, without proof, we are stating that these are all the signals that are required to represent the entire complete basis set. Okay. So, as long as we are taking that to be true, we know that this xt can be represented with respect to these things. So, now it is very simple. All we have to do is this gt must be a summation of some coefficient, let us say that is Cn e to the power j 2 pi f0 nt, and n goes from minus infinity to plus infinity. That is famous Fourier series representation, where the Cn must be evaluated with the same criteria of complex. So, that must be integrated over that period gt into complex conjugate of x. That is where the complex conjugacy comes into picture, and that is why it becomes e to the power minus j 2 pi f0 nt dt divided by the this into complex conjugate of that. So, they will actually cancel each other, it will be just 1 dt 0 to t0. So, that becomes just 1 by t0. So, this becomes 1 by t0 0 to t0 gt e to the power minus j 2 pi f0 nt dt. This is the reason why in the inverse 1 or the coefficient 1, whenever you calculate, you have to put e to the power minus j, and whenever you are actually representing gt, you get e to the power plus j, and you will see later on will from this series we will go to Fourier transform, and that is why Fourier transform always gets e to the power plus j and inverse transform always get minus, or vice versa. Okay. So, this things happens due to that reason. So, now what we have seen that we can represent any signal again with respect to another basis set which are complex. In the next, what we will try to do is we will try to get a relationship between these two representation, what the exponential Fourier series tells us and what the trigonometric Fourier series tells us, and what are the relationship between these two things.